Today we're going to talk about pointers. In order to aid our discussion of pointers, we're going to use this crude memory model over here. So each of these squares is a byte, and starting from here, this will be the very beginning of our memory with address 0. We're going to assume that a word or a memory address is 32 bits long and that our access into this piece of RAM is byte aligned to the size of a word. So every 4 bytes we've written the addresses on here. So 0, 4, 8, 12, 16, 20. And that just corresponds to the number of bytes into our memory block. We've written this so that we start with the lowest memory address down here and the highest memory address 44 up there. I've done this because this is typically how the program space or the memory space of a program would be written. So pointers have a bad reputation in that they're feared sometimes by people. I think it's one of those irrational fears. They're not really that complicated. It's usually, I suppose, if someone's just trying to get something done and they don't want to know this stuff, and then they find out that they have to know this stuff to get it done, they're probably frustrated and probably block their own learning of it. In which case they're probably better off using a language that doesn't use pointers. Or growing a backbone and actually putting the work in to learn it. I'm just kidding. Anyway, so in order to explain pointers, although we've already covered them in the char array episode last time, and before that the dynamic array allocation, I'm going to assume you're familiar with arrays, but not necessarily with pointers, in case you've just come in here and want to know about pointers. So let's just consider a simple variable declaration, and we're going to say that this is wrapped inside our main function, and this is important because it determines main over here. And if we had a single variable called a, now let's think about where this is going to be in memory. The way that a program is organized is you have a text segment, a data segment starting from the bottom, uninitialized data, and then you have the heap, then you have kind of unused memory, then you have the stack. Variables that are placed on the stack grow from the top of memory downwards. So the first entry in the stack would be the top of memory. Actually, you might have environment variables and stuff above that, but let's ignore that and just say we've got the stack here growing downwards and the heap here growing upwards. Dynamically allocated memory goes on the heap and grows upwards. Local memory goes on the stack. So every time we call a function, we put local variables on the stack. And what that means is they're going in consecutively lower memory addresses. So in the function int main, because this is a function, int a is considered a local variable and will go on the stack. Things declared outside of that would be uninitialized and would be before the heap at the bottom here. That means that a occurs in memory. So where is it? Well, what we'll say is that a is here at address 44. And because our word size is 32 bits, we're assuming an integer is 32 bits, and the integer a consumes these 4 bits. Simple enough, right? I mean, don't worry about this layout thing if it's confusing you at all. You can definitely agree with me, I hope, that a has to be somewhere in memory. So let's say it's at address 44 in memory. Now we could create a pointer to a very easily. We would say int pointer ap equals, and then we use this ampersand operator a to get the address of a. And what is the address of a? Well, we've just said that because it was here in the stack frame, it was address 44. So the integer pointer ap actually has the value 44. So it has this value, 44, and it's just a memory address. And a pointer is always a memory address, and it just points to a particular memory location. So in C, a pointer is always a memory address. The type of the pointer determines how we interpret what is at that memory address. In this case, the type of the pointer is an integer. So when we go to that memory address, the compiler knows that any operation that requires the value at that address, that dereferences the pointer, to use the correct terminology, must treat what's at that memory address as an integer. So we only use the type of a pointer when we dereference the pointer, when we want to obtain the value that's at a particular memory address. Now, we've just created another variable, right, called AP. So where is AP? Well, because in this case it's going to be on the stack frame for the main function, it's actually going to be here. So this is A, and our AP is actually going to be here. And it will have the value 44 in it. Whereas our integer, okay, we'll give our integer a value just to be kind of clear. We'll make sure the value is way outside of our memory address, like 101 or something. So in A is the binary representation. Those 4 bytes contain the binary representation of 101. In AP, there's a binary representation of the number 44, or the memory address 44. So the crucial point here is that, of course, AP is also a variable, so it also exists in memory. So what we can do is we can then say, well, what is the address of AP? And then that gives us a pointer to a pointer, right? So if we take the address of AP and of course now we've created another variable which is now going to be here in the stack frame, and what's in there is the address of AP. So the address of AP is the value 40, so this has the value 40 in it. So I've just magically changed clothes, I've just magically rewritten everything on the board. Now what I want to do is, we've kind of got ourselves into one of these scary situations where we're talking about pointers to pointers. And I want to get us back. So you've seen that you can take the address of a variable and get a pointer to it. And you can even take the address of a pointer and you get a pointer to that, which is just another address. I want to go the other way and go from a pointer to something back to the value of it. And we've got 2 steps to go through if we start here. You know, obviously if we took this pointer and went to the value, we'd get to A and we'd get 101, but we've got to go through APP. In order to take the value that is at an address that a pointer points to, we need to do the following. We need to use what's called the dereferencing operator. Confusingly, the dereferencing operator is also the asterisk. And perhaps it's not confusing because it's easy to remember, I guess. It's used twice. And what we're going to do then, we're going to go from APP and we want to go back to a single pointer. Instead of a pointer to a pointer, we want to go back to a single pointer. So we're going to dereference APP to get back up 1 step. So we're going to have a variable and we'll call it APPD, dereferenced APP. It's got 1 less asterisk. And we're going to dereference, so we use the asterisk again, and we're going to dereference APP. So how does this dereferencing operator work? Well, what we do is we take the value of the variable first. That's what it first does. APP is a pointer, which means its value is a memory address. That memory address, we made it point to AP, so the memory address stored in APP is the value 40. We then go to that memory address. So we go to whatever the memory address is that's in the pointer. Now we need to interpret what's at that memory address, because we're trying to obtain the value that's at that memory address. In order to obtain the value, we need to look at what is the type of the pointer that we're dereferencing. Well, the type is a pointer to a pointer, which means that the type that we want to return, i.e. the value of this, is everything to the left of this asterisk. So it's an integer pointer. The value we're getting is an integer pointer. And of course a pointer is just a memory address. So the value we're getting is another memory address, and it's the value of AP, which is the address of A, so it's the value 44. So this will now contain 44, and it is identical then to AP. And then if we dereference that again, so we're going to do APPD dereferenced. So we dereference APPD, then what happens? Well, we said that this is just pointing here. So we take the value of that. The value of the pointer is 44. So we go to that address, and then we need to work out how do we actually interpret what's at the address. Well, we look at whatever it is to the left of the asterisk of the value that we're dereferencing, because we're dereferencing this pointer. And you can see that it's an integer. So we then take the integer value of the bytes that start at address 44, and an integer happens to be 4 bytes long. So we take that value, and now APPD will contain the value 101, because we've obtained that by dereferencing the pointer to a pointer twice. We can easily flip between the pointer and the value just by dereferencing and then taking the address and doing that repeatedly. I wouldn't worry too much about this, but I'm going to show you an example now and to show you that dereferencing cascade. So let us start by declaring an integer variable a that has the value 101. We can obviously just print out the value of this integer as normal. And we'll do that, and we'll just do this in steps. So there you go, it has the value 101 as we expect. And now what we can do is create a pointer to that variable by taking the address of a using the ampersand operator. Now we can print out the dereferenced pointer. So we dereference AP, and from what we said, that's just reversing the ampersand operator. So we should get the value 101. Let's try that out. There you go, we get the value 101. And of course what's happening there when we dereference this pointer, we go to the address that's of the pointer, which is the address of A. So we go there, and then the way that we interpret what's stored in that address, we look at what's to the left of the asterisk, and it's an integer, so we know it's an integer, and we interpret whatever's there as an integer. And since these are now reversible, what we could also do then, we could say we'll take the address of the dereferenced AP, and then we'll dereference it again, which is kind of a bonkers thing to do, but we can do it. And we can do that as many times as we want, because in each step we're taking the address, then dereferencing it, taking the address, then dereferencing it. And I know this looks a little bit insane, but it's just a way to illustrate that each time we apply this operator, and the precedence is applying left to right onto the actual pointer. So we're dereferencing the pointer, then we're taking the address, then we're dereferencing it again, then we're taking the address, then we're dereferencing it again, then we're taking the address, then we're dereferencing it again. You know, we're repeating this process of taking the address and dereferencing it, and we can do that as many times as we want, and we're always going to get the same value back at the end of it, because the operation is reversible. Now what we will do is create a pointer to a pointer. So we're going to take the address of AP, which is a pointer, and we're going to dereference APP twice. And this is going to give us our value 101 back again, because we're going to dereference APP, which will give us the address of AP. We're then going to dereference AP, which will give us the address of A. And then we're going to take the value of that, which is an integer. So we'll get back 101 again. There you go. And we can do this as many times as we want. We could then take the address of APP. And we'd have a pointer to a pointer to a pointer. And again, we could dereference it this time 3 times, and we would then get back the same value again. So taking the address of something and dereferencing it are completely reversible operations. Got my jumper back on. Another mechanism by which we can access the value that a pointer points to is by using the array access operator. As we saw with arrays, it's the square brackets and indexing into an array. That is essentially a pointer arithmetic address operation plus dereferencing operation. So let me illustrate that. So in the previous example, we kind of we had our variables up here at the stack and so on. Normally what would happen is, a lot of the time when we're working with pointers, we're working with dynamic memory. So if we allocate an integer pointer, oh Jesus Christ, look at this. Look at what the, I need to get some new pens, right? Wow. Probably absorb through my skin and give me some kind of, I don't know, diseased. Right. Let's get back to it. So if we allocate an int, pointer to an int called A, and what we're going to do is, this is on a, sort of should be on the same line, doesn't really matter. It's going to be malloc, and then we'll say 3 times size of int. If you remember that from the dynamic array thing. And so let's have a look where these variables will actually be. So we know if this was a local variable in our main function, then the actual variable A is going to be here. So this is A. And then malloc will return an address where we've allocated 3 times size of int. In our case, an int is going to be 4 bytes, and it's going to be allocated on the heap, so it's going to grow upwards from lower memory addresses upwards. So it's probably going to be allocated here, in these 3 bytes here. So this is actually, you could say that's A, but the variable A actually just contains an address, and it contains the address 0, right? So A actually just points to here. And this is the array contents. Now what happens when we index an array, if we want the 0th element of an array, then we go to the A is a pointer, so we go to the address of where the memory address that the pointer points to, and then we dereference it at that point with respect to the index. So because the index here is 0, we do 0 times the size of an int, which is 0, and we just take these 4 bytes here and interpret that as an int. If it was A1, we do 1 times the size of an int, which is 4 bytes, which takes us to here, and then we get these 4 bytes here. And A2 would be 2 times the size of an int, which would take us to here. And we get these 4 bytes. And whenever we... So the array operator takes the index, multiplies it by the size of the pointer, so the size of the type of the pointer, right? So the type of this pointer is an integer pointer, so it multiplies it by the size of an int. If this was something else, like a long, then we might go, in fact, in the case of a long would be 8 bytes. So we would, for example, let's say, so index 0 would still be here, but index 1 would start here at 8 bytes. And irrespective of the size of our type, which can be obtained with this size of operator, we will always multiply by the size of that type, multiplied by the index, to get how far into the block of memory we've allocated. So that is how a one-dimensional array will work, and how you can essentially dereference a pointer by using the array operators. Because you see, we're getting the value back here, and what we're doing is we're looking up the address, adding on 2 times the index times the size of the pointer type, and then we're taking the value. So we're kind of doing an address operation and then doing the dereferencing. While we're here, so while we're here, I will say, so let me redraw that. Another way you can actually do this then is you can dereference A. And if you dereference A, what you actually get is the value there. So when you dereference A, it looks at the memory address, it looks at the pointer type and says, okay, you want an integer, and it will give you whatever value is there. And what you can do is you can kind of behave like an array and do address arithmetic on pointers. So you can say A equals A plus 1, or A plus equals 1, or whatever you want, A plus plus. And then A will now point to here if you do that. Because it knows that the size of the pointer is an int, and it knows that when you say to add 1 to the pointer, you don't add 1 to the actual 1 byte to the address value. The address value is incremented according to the size of the pointer. And this is called address arithmetic or pointer arithmetic. And you can do that in pointers, which is great. So you could dereference, you could do A plus 2, and then dereference that, and get a value back. So let's take a quick look at that in code and just kind of make that clear. So we just got a makefile with our default of pointer array, and then our file pointerarray.c here on the left. So what we'll do, as we said, was we'll allocate 3 times size of int. And I'll tell you what, we will put some values in there, otherwise it's kind of difficult for us to see what's going on. So you know you can access it like this, right? So we'll have 33, we'll just explicitly assign these 3 values, 55 and 99. Oh no, we should have 66, shouldn't we? So that numerically it's pleasing. Now what we can do then is, it might be interesting for us to look at the actual addresses of these 3 elements, just so you can see what's going on. So we can print out the address as an unsigned, as a long, because it's a 64-bit value, the address on this machine. So we're going to print it out as a long, which is also a 64-bit number. But we only really care about the last few bytes and the last few digits of the number, because we're just looking at byte changes. But anyway, so what we can do is we can say, let's have a look at the address of A0, and we'll print that out. And we'll print out the addresses of A1 and A2. I think that's fair. Right, we'll do that. And we're going to get warnings when we do something like this, because we're passing in an integer pointer and we're trying to print it out as a long, unsigned long. But in this particular case, we know what we're doing. We want to do this. There is a %p modifier, which is specifically designed to print an address out, but it prints it in hexadecimal, and I'm not sure if you're familiar with hexadecimal, so we're just going to use decimal for now. Anyway, that is compiled, so the warnings are just warnings, they don't stop the compilation. And let's have a look. So A0 is our first address, and that's actually just the address of A. And what you'll notice here is that the address of 1, we are 4 bytes on from the address of 0, and again we're 4 bytes on from the address of 1 when we look at the address of 2. That's because an integer on my system is 4 bytes long. So, and what I can do is I can print that out. So I can print out size of an int as an int, size of int. Compile that, again it will just ignore the warnings. And there you go, size of an int is 4 bytes. So you can see that this address, all we're doing when we dereference like this is we're getting the base address, and then we're multiplying the index by the size in order to get the next address. And that's how arrays work in C. Let's change it then. We'll change it to a long so that we can see what the difference is there. Just so you can see that this is independent of whether or not of what the type that we're using. So I've changed everything to a long now. Recompile it, ignore the warnings. So our base address is here, and if you look, we are 8 bytes on from there, and again we're 8 bytes on, and that's all the array dereferencing actually does. Let's go back to an int, and we will now look at using the pointer arithmetic and show that we've got essentially the same thing happening. So what we're going to do now is we're just going to actually just print A. So not the and of course this is because this is an address and we're not dereferencing A, we should just get the same as A0. So let's just check that we get that. And we'll ignore the warnings again. Yep, so there we go, A is the same. Now, to show you the arithmetic, so we can say A plus 1, right? And of course, if this was actually just done numerically, we'd expect this to come out as this number, but ending in 225, right? But because it's pointer arithmetic, it won't. Now let's see if it behaves as we expect it to behave. Now there we go, A plus 1 is 228, because 4 bytes have been added on, because that's the size of the pointer type. You know, and we can do that as much as we want. So A plus 2, again, it's another 4 bytes added on. So you can use pointers, and this is called pointer arithmetic. So we're taking the address, and when we add to it a number, we're not adding that actual number to the address in terms of bytes. We're adding on that number times the size of the pointer type. So in this case, size of int, which is 4 bytes. And you can dereference these values as well. So we could say, if we wanted to see what the actual value is, we could have a look at, we're going to dereference A, and yep, and we'll just print that as an integer. And we'll dereference as well A plus 1 and A plus 2. And ignore all the warnings. And what you can see here is, of course, is that A dereference is our value 33, which is a value that we put in there. A plus 1 dereference is 66, and A plus 2 dereference is 99. So I hope you can see then that address arithmetic and array indexing are quite closely related, and that essentially they're just multiples of whatever the pointer size is, and that's how it works. Right, I hope that was clear. Now what we're going to do is look at a two-dimensional array, so a pointer to an integer pointer. I'm going to look at how that's represented in memory. You'll notice I've added a bit more memory because I realised that I can't really do this how I like it unless we add more memory. So we've got 12 more bytes of memory up there. Now what we're going to do then, so we declare our integer pointer, well, pointer to an integer pointer, A, and it's going to be equal to malloc 3 times size of, and it's the type of that we're allocating is an integer pointer. Now, so let's have a look at what's going on in the memory. So A is a local variable to main, so A is going to be at the top of memory, and it's going to be here in our model. So A is here. And what's the address returned by malloc? The address returned by malloc is going to be at the start from the bottom of the heap and grow upwards. And it's 3 bytes long, so it's going to be these first 3 bytes. So A is actually going to point here. So A is going to contain the value 0, and it's going to point to these 3 bytes. And the reason it's, sorry, not 3 bytes, 12 bytes. These. Because the size of an integer pointer, well, an integer pointer is just an address. And if we assume a 32-bit machine, then the size of this is 4 bytes. 32 bits is 4 bytes. And so there's our 3 times 4 bytes, which is 12 bytes. And of course on a 64-bit machine, all our pointers will be 8 bytes long each. Alright, so we've got that now. And before we did something, I don't know if you remember from the dynamic array tutorial, we did something like this. For int I equals 0, I is less than 3, I plus plus. And then inside there we said AI equals, and then we're going to have malloc 3 times size of int, and then we're going to close the bracket. I know it's very small, but it's just, we're just allocating for each of the array indices 3 times the size of an integer. So what's going to happen when we do that? Well, what's going to happen is we're going to go first of all to this part of the memory address at A0, and we're going to allocate some memory. And this is going to be allocated on the heap. It's going to be 3 times size of int, and int is 32 bits on our system, our imaginary system, 4 bytes. So we're going to allocate these three blocks, these 12 bytes. So this then is going to point to here. This is going to contain the value 12 because it's going to point to this memory address. Then we go to A1, and A1 is going to be here, and that of course is then going to point to this block. I know it's getting a bit confusing now, and of course then this last block, which will be indexed A2, is going to point to these. So we're getting very confused. It's getting a little bit confusing on the board. Let me just check. But I'll tell you what, let's try and do this in a clearer way. So we're still going to have our A pointing to, we'll go down here. So A is still pointing to here. And then we'll just use different colours. So we can get away with this one. So the first element's going to point here. Then the second element, these 4 blocks, they're going to point to address 24. And the final element, these 4 blocks, they're going to point to, so these 4 bytes, the address that's stored there is going to point to address, it's going to be the value 36, and it's going to point there. So, as you can see, it's not actually that complicated when you look at the memory layout for something like this. Because in the first case, our 3 integer pointers are stored here, and then each of these points to another memory address, which then stores 3 integers. So that's the 2-dimensional array using pointers. And of course, and you can see that when we index here, we're multiplying by the size of a pointer. So we're going, and our pointer is 4 bytes. And if we were to do a kind of 2-dimensional index, so say we did A0, 1, what would happen is we go to A0, so there's no multiplication. Okay, we'll put a multiplication in there. So say we want A1, we multiply by 1 times the size of an integer pointer. Well, an integer pointer's 32 bits, so we go to here, then we go to that block, and then we've got another 1 here, but this time we multiply by the size of an int, but it happens to be the same size, so we'd go here and we'd retrieve the value that's stored there. Now of course, if we had longs in there, each of these blocks would be twice as big. If there were each of the elements would be 64 bits, and when we would index with 1, instead of multiplying by 4 bytes and going to here, we'd multiply by 8 bytes and we'd go to there. Alright, I think we're almost done with pointers, but I just want to talk about one more thing, which is passing the values of pointers around. So if we had passing them into functions and returning them from functions. So if we had an integer pointer A, which we've malloced as 3 times size of int, then what happens when we pass that to a function? So let's have a look. So again, we've got A here, it's our 3 bytes here that it points to. So the variable A contains the value 0, points to that address. If we have a function here, we'll just have a void function f that takes an integer pointer, or p, what's going on here? What value do we get inside the function? Well, the value we get inside the function is, we don't pass in like the whole array, we're just passing the pointer, which is a memory address. So if we were to call this function like fa, p here would just have the value 0, because it's just the address, it's just an address. And so we always pass just the address. This is important because what the function f what you might want to do inside the function f, you might want to reallocate the size of this, right? You might want to do a realloc and change the size of a, and because of course within f you can do things like p0 equals 5 or whatever, and in that case you're actually modifying a, because of course we go to that memory address and we modify the thing at that memory address, that will work. But if you were to try and do something like p equals realloc and then some parameters, and assume then that you're going to change the size of this, you won't. And the reason you won't is because this is just pointing to a memory address. When you do your realloc, only p is going to be changed. And p is a local variable, local to this scope. It's just a local variable that has the value of the memory address. So it just has the value 0 in it. And then you're just changing essentially a pointer variable to have this new memory address, and that will do nothing to this value because it's outside of the scope of the function. If you wanted to do that, you would have to change the value stored here. And in order to do that, you would need to know the address of here in order to modify it. So if you wanted to do a reallocation, you would have to redefine your function so it was something like this. And we're going to have a pointer to a pointer instead. Oh, it's called p, right? Now, and then you would do something like f, and you could take the address of a. Now what you would be passing in is the address of a. So you'd be passing in the value, this is byte 56, right? So you'd be passing in the value 56. And then if you did something like p equals realloc, you would want to do this. The value of p equals realloc. So you would go to the address that p points to, and p is now pointing to 56, right? Because we took the address of a. And then we change the value of it, what's stored in there, which is the memory address of our array. And then we would have also changed a, because we're actually going to a's address. We're dereferencing it, we're changing the value at a's address, right? So I hope you can see that. I'll show you a quick example of that in code, and then we'll just do a summary of the pointers. So we've got a new program here then called pointer pass. And what we're going to do then, we're going to have our function, and to begin with let's just call it then f, and it takes just a normal, so it's a void, returns nothing, and it's going to take this pointer p, integer pointer. Now if we declare a variable a, and it's going to be 3 times size of an int, so there's our integer pointer. I'm just going to call f with the parameter a, and what I want to do is let's print out the address of a, okay? Or we just print the pointer a, right? And as a unsigned long, and we're going to do the same thing inside the function. And let's have a look. Again, we get warnings because we're trying to, it's an integer type and we're trying to print it as a long, but we're going to ignore those warnings. So the address of a, or a, the pointer a is an address, right? It's a pointer, it's an address. So when we print it, we get that address. When we pass it into a function, we get that address. So if we were trying to change the address of
of our array. We're trying to change the size of our array, and we did, we'd probably use a temporary value, right? But let's just assume that the reallocation works. I mean, if you look at dynamic arrays, you'll see that normally we use a temporary value. We want to change it to 6 times size of int, because we want to increase the size. We'll print p again just to see what happens to the address. We'll just start like that, right? And we'll ignore the... oh yeah. We're reallocating p, and we're changing it to 6 times size of int. It's quite annoying with those warnings, but we'll just have to put up with them for now. You can get rid of them, but we'll leave them on. And what you can see is that now, after the reallocation, p is a different value. So we've reallocated p, but what about a? Let's call the function and we'll print out the address of a again. So first of all, this is a before, there's its address, and then we passed it into the function f, and here's its address. Now we're reallocating p, but oh look, the address is the same for a afterwards. That's because we haven't changed a. We've changed the local variable p. We've just changed its value. So we haven't changed a at all. If we want to change a, we need the address of a. We need to go into a and change a's value. You know, if you see what I mean. This is just a local copy of the value that a contains. So let's do it then. So instead of, we'll actually pass in a pointer to a pointer, and we're going to say, we'll print out the value of the pointer, and let me just get rid of this stuff so we're not getting confused. So a before f, a after f, and we're going to pass in the address of a instead. And we're going to print out the dereferenced p. Now we're going to reallocate, and we're going to reallocate by dereferencing p, so we're going to the address of a. So then we're changing what's stored in a. We're changing the address stored in a. Out. Of course, so realloc needs the address that we're trying to change, but we're not trying to change p, we're trying to change the thing that p points to. Just compile that and then run it. And now what we'll see is, so a before f, so this was the address beforehand. Then we call the function p with the address of a, and the address dereferenced is this. And now we're changing the value that's stored in a, because we passed in the address of a. So the address of a dereference gives us a, and we're changing the value of a. So the value is now changed, and then if we print the value of a afterwards, we can see that a is changed as well. So we have to pass in the address of a and dereference the address of a to manipulate a if we want to do, for example, a reallocation within a function. So just to summarize about pointers, we can have we declare a pointer like this, and a pointer is just a memory address. We can set a memory address explicitly if we want, but most of the time we won't know what the memory layout looks like. Most of the time we get our addresses from malloc. But we could do this. The variable a would be here up in the stack, and we could set its value to 12, so that then we would say that a points to here. Right? We can take the address of any variable, and we can take the address of a pointer, and that will return a pointer to a pointer. Of course, the pointer to a pointer is still a variable, it will be in memory somewhere. And the value then in this particular case, we've taken the address of a was at address 56, so the value in here, in this variable, will be the value 56. When we increment pointers, so if we do a++ to add 1 to a pointer, the pointer will be incremented by the number of bytes which is the size of the pointer type. So an integer has 4 bytes, so if we increment a, we're going to end up here. So this is a plus plus, right? That's its address. When we dereference a pointer, we get its value. So if we dereference a, we'll get the value stored in here. We haven't actually put anything in there. We could put something in here by assigning to it. So you can assign to a dereference pointer and it will change the value at that address. Of course, you wouldn't do this in practice because we need to manage the memory. We can't just pick random addresses and start messing around. We need to call malloc to get an address, but this is just for illustration. When we use array indexing, we take the index, multiply that by the size of the type, size of the pointer type, and then we dereference it and get the value. When we have a multi-dimensional array access, and in this case this doesn't make any sense because we've only got a single dimensional array, but imagine it was a 2-dimensional array. We dereference the first, we perform the address arithmetic for the first pointer type to get the address for the second part, and then we dereference the second part according to the index and according to its pointer type. To determine the type of a pointer, we look to the left of the asterisk. So in this case we'd have an int, so this is an integer, and any address arithmetic is going to be multiplying by the size of an integer. In this case we have an integer pointer, so any address arithmetic on AP is going to be multiplying by the size of an integer pointer, which is going to be the size of your memory address. So 32 bits on a 32-bit machine, 64 bits on a 64-bit machine. If we had something like that, the size then of our pointer is going to be this, which is a pointer to an integer pointer. But because it's a pointer, it's just a memory address again, so it's still going to be 64 or 32 bits, depending on the architecture. And we can continually dereference either by stacking asterisks before the variable, so that would be 3 dereferences, actually just 2 dereferences, or you can dereference by stacking brackets after. There's probably just one more thing I want to say. There's a special pointer type called null, which is usually the value 0, and that is often returned by functions in the case of error, or you passing in a null pointer, what's called a null pointer, is also a special case. There's also something called the void pointer, which is a pointer that has no specific type to it, and a void pointer will always just be the size of a memory address. So a void pointer will always be 64 bits or 32 bytes. Right, that's all I want to say about pointers. I hope that was useful, and hopefully you've learned about pointers, how they relate to the memory address. And of course you don't necessarily need to know all that to use pointers in practice, as long as you know how to dereference them and how you can change them and things like that. And what they are, which is just values, they're just memory addresses. But hopefully that's a good starting position for you at least. Alright, well thank you for watching, and I'll see you next time.